So in this video, I'm going to discuss the speed of electrons, how fast the electrons flow, and the difference between actual flow of electrons, which is called drift velocity, and what we see, how fast the light turns on. Okay, so there's a difference between the actual flow of electrons, drift velocity, and how fast you can turn on the switch and light turns on. The flow of electron is a current. Current is the flow of electrons, and we know that it's the electrons that's responsible for the electric charge. For a typical wire, we use copper. So we can find out how fast those free electrons inside the copper flow per how fast they flow. And this actual flow of electron is called drift velocity, the net flow of electrons. So they actually, if you have a force, electric force will be turned on if you have an electric field. If you have a potential difference, you're going to have an electric field and electric potential, the force, and then therefore the electrons move. And how fast these electrons move inside a copper. So here I did a little bit of a calculation, which you're not responsible, but if you're interested, you can see how fast actual flow of electrons in a copper wire. So let me share the screen. I already did the calculation. Okay. So only if you're interested. How many, let's find out first of all, how many electrons are in a copper, free electrons in a copper. So how fast electrons flow in copper wire, and the actual flow of this electron is called drift velocity, all right? So example, copper. Copper has atomic number 29. That means it has 29 protons in a nucleus, and therefore 29 electrons in shells. And first shell can contain up to 2 electrons, second shell can contain up to 8 electrons, and the third shell can contain electrons up to 18 electrons. So therefore, copper has 129, so this is 2 plus 8, 10 plus 18, so 28 electrons are in up to third shell. So the last electron in a copper will be in a fourth shell by itself. So copper has one free electron in a copper, okay? Then copper's mass density, which is the how many grams per cubic centimeter, is a 9, there is about, copper weighs about 9 grams per cubic centimeter. Atomic weight is that how much it weighs per 1 mole. 1 mole is that called Avogadro's, you can find it by Avogadro's number to see how many atoms in per mole. So if you have a 63 point, if you have a 1 mole, which is the unit the chemists use, you have a 64 grams of copper per mole. And in 1 mole, you have a 6.022 10 to the 23 atoms. Okay, so combining all these, you can find out mass of the copper for whatever the geometry. So let's say I'm looking for the copper wire that's a 1 millimeter diameter and a 1 meter long wire, right? 1 meter long wire, it's about this much. 1 meter long wire, and then a very small 1 millimeter long diameter. Then the mass of the copper for that long wire is 9 grams. Okay, I did the calculation here. And so that's the 9 grams it has, that's how much it weighs, the wire of a copper wire. And how many number of electrons in that wire will be putting all these numbers here, okay? Density, and then how many numbers of atoms per mole, and therefore you can find out there are 8.4 times 10 to the 22 electrons per meter for 1 millimeter diameter wire. So per section per meter, there are 8.4 times 10 to the 22 electrons. All right, for the cup, such a 1 millimeter, 1 millimeter square diameter wire, copper wire. All right, then here, let's see, if we were to have a 1 ampere, by definition, 1 ampere means 1 coulomb per second. And electrons have 1.6 times 10 to the minus 19 coulomb, right? So therefore, for 1 coulomb, you have to have a 6.3 times 10 to the 18 electrons. That's how many electrons per coulomb. That means for 1 ampere, you have 6.3 times 10 to the 18 electrons flow per second. That's what it means by 1 ampere. 1 ampere means you have a 6.3 times 10 to the 18 electrons flow per second. Then we will consider this particular wire, the copper wire, right? How fast the electrons in this copper wire flow when you have a 1 ampere current flowing. Then you see here the drift velocity, which is the velocity of a copper, is 7.5 times 10 to the minus 5 meter per second. It takes 3.7 hours to travel 1 meter long wire. That's the actual flow of electrons. So imagine that you have 1 millimeter square diameter and 1 meter long wire, copper wire, and you have a 1 ampere of a current flowing. That's how fast the actual electrons are flowing. 3.7 hours to travel 1 meter. Okay, if you want to take a screenshot for this, you can, let's see here. Okay, take a screenshot if you like. Okay, took a screenshot. So let's see. So that's a long time, right? Does it take? So when I turn on the switch for the light, let's say that from the switch to my light, maybe it's not even a 1 meter long wire that's connected. Does it take, do I have to turn, after I turn on the switch, do I have to wait for like a 3.7 hours for the light to turn on? No. No. So then did I do something wrong with my calculation here? Well, you can take a look at my calculation and tell me if you find a mistake. But drift velocity, the actual flow of electrons, is very, very, very slow. It's very slow. Extremely slow. But that's not how things go. When I turn on the switch, almost instantaneously, the light turns on. Right? So let me just, I can come back here. So if I turn on the switch, light turns on. We don't need to wait 3.7 hours or even 6 hours for the light to turn on after I turn on the switch. So then what's happening? See, similar thing, you can think about it. Their electrons are in everywhere along the wire, right? And there are electrons everywhere. All you need is to have a signal that to know that they have to move to be sent. So therefore, they can move. At the end of the wire, so here's the long wire here, right? And then a light bulb is connected here. So at this very end of the wire, there are electrons, free electrons still. All you need is these electrons to feel the electric field, then move, then turn on the light bulb. Same thing happens with the water. When you open up the water nozzle, turn on, do you have to bring a water molecule all the way from the up in the Sierra or in a water tank? We don't need to wait for the water molecules to actually come all the way up from crystal geyser or all the way up in a water tank to come up on your faucet. water molecule is already there. All you need is turn the nozzle, then water molecule at the end of the faucet feel the pressure difference, which is the signal to feel the force, so then it comes out. Water molecules is already there. Same thing happens with these electrons. The actual flow of electrons can be slow, but electrons are already there. Electric signal, electric field travels very, very fast. About 3 times 10 to the 8 meter per second, which is almost instant. So I turn on the switch, electric field travels that fast, 10 to the 8. And then free electrons at the end of the wire connected to the light bulb moves, light turns on. That's why instantly light turns on. Same thing as the water. Water molecules is already at the faucet, the end of faucet nozzle. Then you turn, water comes out. You're not bringing the water all the way there. So the drift velocity of electron is very, very slow. I also asked my family to do another demonstration. Okay, so let's see. We keep making all this demonstration video. Hope you are enjoying it. Let's see. So first, what I asked everybody to do was to tap the shoulder. Tap the shoulder. When the first person tapped the shoulder, each person taps the shoulder. Dun, 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 dun. So this is more like a drift velocity. One electron moves, another electron moves, another electron moves. So that's drift velocity. And then secondly, what I asked was, I raise my hand. So as soon as you see me raising hand, the light signal travels. The last person in the line, see me raising hand, then raise the hand, and that's almost immediate. Okay. If you enjoy. Thank you. So you see how fast light can travel, electric field can travel, 10 to the 8, and then the person at the end, all you need is a person at the end of the line to see that signal to move. You don't need to wait everybody's to come along. You just need to get the signal to move. So that's why the light doesn't take 3 hours or 6 hours to turn on. All right, so there's a difference between a drift velocity and actual flow of electrons. If you want, I can show you quickly. Here. Okay, so free electrons inside the wire. Sorry. So free electrons inside the wire. So there's the free electrons E minus inside the wire, because you have some kind of a temperature. So they're constantly, randomly moving. Maybe I don't like this. They're constantly, randomly moving, right? Free electrons. Because of they have a kinetic energy. Let's say it's like this. Something like that. It's randomly moving. So this is the one, this line is no electric field. But as soon as it feels the electric field with electric field, you still have these random motion, right? But it'll be a little bit biased. So as soon as it feels the electric field, this random motion of electrons will be moved like something like this. So there is a little bit of a shift. Still it's moving randomly, but it gets shifted. So it drifts. It drifts towards the electric field, actually opposite to the electric field because it's electrons negatively charged. And that drift that continues, then actually it has to travel all the way to 1 meter. It takes 6 hours. But immediately, as soon as they feel the electric field, all these free electrons will be gets biased immediately. So that's why the light doesn't take 6 hours to turn on. Okay. So again, the drift velocity is very slow. Drift velocity is the actual flow of electron. I'm going to come back. So the drift velocity is the actual flow of electron, which is very, very slow. But what you need is the electric field signal to travel fast so that you can turn on the light bulb immediately. All right. So that's about it for the actual flow of electrons. Hope you enjoyed it. I'll see you in a discussion.